Hello everyone. Today I am going to start chapter 2 of hydraulics, and name of this chapter is kinematics of fluid flow. So before entering to this chapter, let's know what is kinematics of fluid flow or fluid kinematics. So it is the study of fluid in motion whenever the fluid is in motion, where pressure forces are not considered. This is known as kinematic fluid or fluid kinematics. So this is the outline of this chapter. This also outline. So in this chapter I will discuss article wise, as if I discussed like this, then it will be better for you to understand and to clear. It is more clear. So let's discuss the article 2.1. This is basic equation of fluid flow and their application. So first is rate of flow or discharge. So it is defined as the fluid flowing per second through a channel or section of pipe, and it is expressed as shown here like capital Q. So mathematically we can say Q equal to A into V. This is the area of cross section, V is the velocity of flow. So its unit we can say meter cube per second or centimeter cube per second or millimeter cube per second or liter per second. Next is continuity equation. So the continuity equation is developed based on the principle of conservation of mass, and this equation states that the rate of fluid flow through the pipe is constant at all cross sections. That means the quantity of fluid per second is constant throughout the pipe. So this equation says A1 V1 equal to A2 V2, and that means the discharge at section 1, if we consider, see this figure, this is the direction of flow. If we consider this is section 1 and this is section 2, so according to continuity equation, the discharge at section 1 is equal to the discharge at section 2. That means A1 V1 equal to A2 V2. Also at every point this is constant. So let's solve a problem based on this equation. Problem is the diameters of a pipe at the section 1 and 2 are 10 centimeter and 15 centimeter respectively. Find the discharge through the pipe if the velocity of water flowing through the pipe at section 1 is 5 meter per second. Determine also the velocity at section 2. So this is the figure, we have to draw it. This is the diameter at section 1 10 cm, this is 15 cm, velocity it is given 5 meter per second, and we have to find out the velocity at section 2 and also the discharge. So two things here we have to find out. Let's see. So as the diameter d1 is given, we can find out A1 area pi by 4 d1 square, this much. B1 is given, d2 this is given, we convert it into meter. 15 centimeter equal to 0.15 meter. Similarly we find here A2 area at section 2 pi by 4 d2 square. So this is this much, 0.01767 meter square. So we know the discharge through the pipe is given by the equation A1 V1. We can also calculate it by applying A2 V2, but here V2 is unknown, so we only apply the discharge formula like A1 V1. So we find here this much. After multiplication, the answer is 0.03927 meter cube per second. Using the equation, or we know, or by applying the continuity equation A1 V1 equal to A2 V2. So here V2 is unknown, so V2 equal to A1 V1 by A2, and by applying this we find 2.22 meter per second. This is the velocity, this is the answer. So similarly you have to solve more problems based on this continuity equation. Next is Bonolis theorem or Bonolis equation. This is the most important thing. So According to Bonolis theorem, for the streamlined flow of a non-viscous and incompressible liquid, the sum of the pressure energy, kinetic energy and potential energy per unit mass at any point of liquid is constant. So, the sum of the potential energy, kinetic energy and pressure energy are constant. This equation is known as Bonolis equation. It has also a derivation. So, by draw this figure, or if we take this pipeline, we can solve or derive the Bonolis equation. Let's take the limitation, some limitation of Bonolis equation, like the above equation has been derived by assuming that the velocity of every element of the liquid across any cross section of the pipeline is uniform, but practically it is not possible, or it is not true. So, the elements of the liquid in the innermost layer have the maximum velocity, and the elements of the liquid in the innermost layer have the maximum velocity. The velocity of the liquid decreases towards the walls of the pipe. So, these are some limitation of the Bonolis equation. Next, see some applications in real life, like airfoil, atmosphere sprayer, blowing of the roofs of the houses during a storm, or Bunsen's burner. So, these are some applications. But if we say about practical application, this is the major thing, also very much important, the practical application of Bonolis equation, like for pitot tube, orifice meter, Venturimeter. So, let us discuss one by one. So, first is pitot tube, or you can say also pitot tube. So, it is an instrument, or it is a tube to determine the velocity of flow at the required point in a pipe or a stream. And a pitot tube consists of a glass tube bent at an angle 90 degree, as shown in the figure, and the lower end of the tube faces the direction of the flow like this. The liquid rises off in the tube due to the pressure exerted by the flowing liquid, and by measuring the rise of liquid in the tube, we can find out the velocity of the liquid flow. So, for calculation of the velocity, we apply the formula like V equal to 2gh. So, let us solve a problem. Find the velocity of flow of an oil through a pipe when the difference of mercury level in a differential U-tube manometer connected to the two tappings of the pitot tube is 100 mm. Take coefficient of pitot tube, this is 0.98, and specific gravity of oil, this is 0.8. So, let us solve it. So, your differential of mercury level, this is we consider as x equal to 100 mm, we convert it into meter, this is 0.1 meter. Specific gravity of oil S naught, this is 0.8, specific gravity of mercury, this is Sg, we can say 13.6, it is fixed. Cv, this is given 0.98. So, here the velocity formula is Cv into square root of 2gs, but h is unknown. So, this is the formula to find out h equal to x into Sg by S naught minus 1. So, all the values are given here. Finally, we found h equal to 1.6 meter of oil, and at last the velocity of flow, this is after putting all the values we found 5.49 meter per second. Similarly, you have to solve other problems. Next is Venturimeter. So, this instrument or Venturimeter is used for the measurement of flow rate, that means discharge. In this case, we measure the discharge. It is generally used for large diameter pipe. So, here the formula is for the calculation of discharge, this is Q equal to A1 A2 by A1 square minus A2 square, square root of A1 square minus A2 square into square root of 2gh. This is the theoretical discharge, but actual is CD into A1 A2 by square root of A1 square minus A2 square into square root of 2gh. actual discharge will be less than the theoretical discharge. So this value or actual discharge through the pipe is always less than the theoretical discharge value whatever we calculated from the given data. So let's solve a problem. A horizontal Venturimeter with inlet and throat diameter 30 cm and 15 cm respectively is used to measure the flow of water. The reading of differential manometer connected to the inlet and the throat is 20 cm of mercury. Determine the rate of flow. Take CD equal to 0.9. I think everything is given in the question. So here we have to find out the rate of flow or discharge. So at the inlet diameter, this is D1 equal to 30 cm. So area we can calculate by applying this formula, pi by 4 D1 square, this much. Again the diameter at throat, this is D2 equal to 15 cm. A2 similarly we found this much. CD is given, and reading of differential manometer, this is X equal to 20 centimeter of mercury. So H equal to, we know the formula, H equal to X into SH by S naught minus 1. This is SH stands for specific gravity of mercury or a heavy liquid, which is given 13.6. S naught specific gravity of water, this is 1. So by putting all the values, we finally found Q equal to this much centimeter per cube, 125,756 centimeter cube per second. And after conversion into liter, the answer is 125.756 liter per second. Similarly, you have to solve more problems, more and more problems based on Venturimeter, Peter tube, also of continuity equation. So for this lecture this much. In next lecture we will continue this chapter, and we will discuss about the third application. This is orifice meter, third application of Bonolis equation, and all about orifice meter. So thank you.